Hello everyone, welcome back to the latest lecture session. Until now we have been discussing how to treat wastewater. In that context we looked at various aspects. First, removing the bigger particles, clothes, rags via the core screen, and then the grit, relatively inert but bigger particles which can be relatively easily settled out. And we looked at sedimentation as our friend in that case, or gravity as our friend, and we looked at sedimentation. And we looked at different kinds of sedimentation, type 1, 2, 3, 4, or different types of settling in the context of sedimentation. Then we moved on to primary treatment, where we wanted to remove the suspended solids. Yes, two issues, one, to decrease the load on your biological system, and also if you have any inert content and such, it's easier to do that. But not all wastewater treatment plants do that. We discussed this elsewhere. So sedimentation, we look at that, again gravity is our friend, and then we moved on to secondary treatment or biological treatment. In that context, the principle was that you had organic content which is relatively reduced form of carbon. So that acts as an electron donor. So if you have an electron acceptor, which is oxygen in this case, you can have the relevant redox reaction, and the byproducts or the products of this reaction will be carbon dioxide. But this reaction is too slow. So what do? We are going to use nature or the microbes to help us catalyze or fasten the kinetics of this reaction. How do we fasten it, or how do the microbes fasten it? They fasten it by releasing enzymes. And why do they want to do that? They need to have a reason for that. Because they want to grow, they need energy. They are going to degrade our waste and gain the energy. And also they are going to use our waste for cell synthesis, right? They need to form cell mass, so they are going to use that, or use the waste for cell synthesis and also for energy production. And after we do that, we saw that flock forming microbes are what we want to form, because you want to separate that from the water. So clarification and then thickening at the bottom of that sludge. Why? Because you want to have sludge with higher solid concentration and less water. Why? Easier to recycle and also easier to treat the sludge later, right? Economical too. So we are done with that organic part, and then we started looking at nitrogen and phosphorus. Nitrogen principle is the same. You have an electron acceptor donor. You want to try to play around so that you can remove nitrogen. Then we moved on to looking at phosphorus. Phosphorus, it was a bit more tricky, not as straightforward as removal of nitrogen, where ammonia was oxidized to nitrates, and nitrates were again reduced to nitrogen gas and removed. In the case of phosphorus, we saw that we want to put the system under stress, or the microorganisms under stress, so that a particular kind of microorganisms thrive, and the conditions are anaerobic and aerobic. In anaerobic, the organisms release phosphorus because they need that particular energy which is given out when polyphosphates are, degraded or transformed, and during that process you have phosphates being released. That energy is used by the microbes to store carbon and electron donor source, let's say, right? And when they go to the aerobic phase, they use this stored carbon or stored electron donor to outcompete the other microbes. So they thrive much better than the other microbes. And during this process, again, they are going to try to store or form polyphosphates. But to form polyphosphates, obviously, you need to take the phosphorus from the water. So if we look at the anaerobic and aerobic phase, net, there is an accumulation of phosphorus. So we can then remove these phosphorus accumulating organisms from the system via the sludge removal, So we were done with that. And the last aspect is disinfection, as in we are still left with some enteric pathogens or enteric microorganisms or pathogens which you want to degrade, or if I may say so, inactivate, so that they don't lead to propagation or transmission of disease once they are let out into the receiving water body. So let's go forth and look at that. So disinfection, right? What were we done with until now? We removed the relatively bigger particles, and then we removed grit. We removed the suspended solids, most of them, and then we removed organic content which we measure by BOD and such. So preliminary treatment, primary treatment, secondary treatment, and then nitrogen and phosphorus, the nutrient removal. This is the tertiary treatment. And finally, we need to take care of the pathogens, right? So when we talk about wastewater, this is what we are typically trying to do, right? So preliminary, primary, secondary, tertiary, and then disinfection. So some treatment plants, especially the older ones, will not have nitrogen and phosphorus removal, but then you can look at upgrading them. So in the context of disinfection, we have different, what do we say, ways to go about it. Some are cheaper, but they do not or are not effective against all kinds of pathogens. Some are relatively more effective, but they are relatively expensive and difficult to, not difficult to, let's say, there is greater technological know-how required to be able to maintain the system. So it's a balance between what you are trying to achieve. Let's go forth and look at what we have. Okay, obviously, what's the goal? The goal is to kill. I guess kill is a layman's term, pathogens, while minimizing the formation of harmful byproducts. Anything that we do, let's say I take a medicine, right, I'm going to have side effects. Maybe the analogy is not a great analogy here, but again, when I add a compound to water, it can also be toxic by itself, or it can lead to formation of harmful byproducts. These byproducts are typically called disinfection byproducts. Disinfection byproducts. So you want to kill the pathogens, but want to minimize the formation of these DBPs. So let's see how we can go about that. Design steps. So you are going to test the unit at specified flow and velocity with test organism. One aspect to note is that, models fine, but when you build the system, you are going to have considerable or, short circuiting. So water that has to spend a certain amount of time would not probably spend as much time in that particular system. But unlike the case of organic removal, where you can have some variation, you don't want to have pathogens being released into the environment. So here, with respect to disinfection, we need to be much more careful about, the variation in the quality of the water, especially in the context of drinking water treatment. That's much more of a concern. Maybe not as much a concern in wastewater treatment though. So that's one thing. So why did I mention that? Because you want to obviously test it at the unit or on the unit with the relevant flow, let's say. Measure influent effluent concentrations of the viable organisms. Use known disinfection kinetic constants, right, for test organism and influent effluent concentration to calculate doses in the system. So obviously, what is coming in, microorganisms, what is going out, right? And if you can find the rate constants or such where the disinfectant will degrade or kill, if I may say so, these pathogens, you can more or less come up with a model to calculate the dose in the system, let's say, right? We have to ensure that the doses measured in the test are adequate for desired removals. So some safety factor and such, but again, that goes into the design, let's say. So chemical disinfection kinetics in general, before we go further, what do we know? We know that A goes to products, first order reaction, first order. Rate is always dependent only on the reactants. So rate of this reaction is dependent upon the concentration of A and the rate constant of that reaction, right? And how is the rate of the reaction going to be equivalent to rate of A? So because it's loss, you can say A by stoichiometric coefficient of A. Stoichiometric coefficient of A here is 1, right? So that's what you have. So here, similarly, in the context of disinfection kinetics, we use similar principle. So what are some of the notations that we are going to come across? Let's look at that. N naught, initial number of organisms, initial number of pathogenic or the indicator organisms that you are trying to measure that are coming into the system, right? Number of organisms remaining at time t, okay? Rate constant of inactivation, so maybe that's a better word as we see rather than kill. Disinfectant concentration that you are trying to put in or maintain. Typically, you will maintain a constant disinfectant concentration. N is the coefficient of dilution, which we will look at later. T is the exposure time. How much time are the relevant pathogens being exposed to that particular concentration in that particular reactor. So, exposure time, let us say, or contact time. So, long ago, Dr. Chick or Chick's law tells us that the rate of inactivation is depend upon that particular rate constant for inactivation and the number of microorganisms. So, N goes to products, you can think of it, again this is an analogy, this is not a chemical reaction here. The rate is like this. So, if you put that into a batch reactor or batch for a batch system, you know that for batch system what is the mass balance? V dC by dt is equal to Q in C in minus Q out C out, this is OUT not plus volume into rate of formation minus rate of loss of that particular compound. Here if I am applying it on a batch reactor on microbes, let us say, which are initially at a concentration of N naught, right. So, this is 0, this is 0, no flow coming in, no flow going out, and rate of formation of the microbes is also 0. So, dC by dt is equal to minus rate of loss, and I know that the rate of loss is equal to Kn. So, dN by dt, I am concerned about the concentration of the microbes. So, instead of C, I am using the term N. N is giving me the concentration of the microbes at a given time in the system is equal to minus K times N. So, I integrate this, I will get Nt or natural logarithm of Nt by N naught initial, this is not out, equal to minus K T. So, that is what we have out here, right. So, that is why we obviously looked at mass balance earlier in the class, right. So, we understand this, you can apply this for a batch reactor, for a continuously stirred reactor, or for a plug flow reactor system, but obviously for plug flow you will not look at retention time, you will look at, you will not look at time, you will look at hydraulic retention time. Again, I think we will look at that later. So, here as you can see, we are not really considering the concentration of the disinfectant, but obviously the concentration of the disinfectant will play a role, isn't it? It can't be such that even at 0 it is going to happen, or even at a dose of let us say 100 milligram per liter of chlorine, you are going to have the same kinetics, let us say. For example, consider the case when we have 1 milligram per liter of chlorine, a common disinfecting agent, and 100 milligram per liter of chlorine, right. But as we saw earlier from Chick's law, it was equal to the rate of inactivation was equal to K times N. There is no term that takes into account the concentration of the disinfectant, let us say C. So, that is what is rectified in this Chick-Watson law. So, we had the rate constant earlier. So, that rate constant is dependent upon Kcw, the inactivation rate constant, and the concentration of the disinfecting agent which you are holding or assuming to be constant in that system, and N is the dilution factor that we considered earlier. So, you can say that R equal to K dash N, where K dash is equal to this inactivation constant times the concentration of the disinfectant raised to the power of N. N was the dilution factor, right. So, what is the relevance of N? I guess when N is equal to 1, both concentration and time are equally important. Okay. So, maybe we will look at this here and then discuss that. So, this is our K dash, right, let me say K dash, and R is thus is equal to this, and similar to the case earlier where we had in the Chick's law, from the Chick's law we know and we derived that for the batch system it was equal to minus K T. Hopefully, I did not make any petty error. Yes, we did not. So, but now K is K dash, which is equal to this. So, that is equal to minus, okay, I should have, okay, Kc K dash, this is K dash. So, that is equal to Kcw C to the power of N T. So, when N equal to 1, both concentration and time are equally important. When N is less than or far less than 1, time or the contact time is relatively more important. When N is greater than 1, obviously the concentration is relatively more important, right? So these are aspects that need to be looked at in the context of the dilution factor n here, right? I think that's what we call n or refer to n, okay, coefficient of dilution. Fine. So this is an aspect. Let me see what else we have. Okay, for a plug flow system, in general, you would like to have a plug flow system. That's something we already discussed, as in why do we want to have a plug flow system. In general, it's more efficient for the same, what do we say, volume of the system. If you can maintain plug flow system, your effluent concentration is going to be relatively lower compared to a CSTR or such. So we looked at that earlier. So how do we come to this? Let's say apply the mass balance. So let's say V dN by dt. I am applying, let's say, the fundamental mass balance equation, dC by dt plus U dC by dx is equal to, say, plus or minus sinks, which is rate of formation minus rate of loss. So I'll end up with at steady state, and x by u is equal to theta. So dC by d theta is equal to minus the rate of loss, and rate of loss I know that to be equal to, and C is n, the microorganism concentration, dN by d theta is equal to minus R L, which is equal to K times the microorganism concentration. What is K? K is nothing but KCW into C to the power of n, right? That's something we saw. RL was equal to K dash n, where K dash is equal to KCW into C to the power of n. So that's what we have, and you substitute and not substitute, pardon me, integrate and so on and so forth. What do you get? This is what you get. Please note that it's similar to what we had earlier as a natural logarithm of n at time theta by n naught or initial n. This is n naught. Let me make that clearer. Okay, so n at theta to n naught or n initial is equal to minus KCW C to the power of n theta. So obviously, if I take this, raise it to the exponential, that's what I'm going to get, and that's what we have here for a plug flow system. But obviously, you see the parallels between the batch reactors equation and the equation from the mass balance for the plug flow system. So that's what we have. Again, this is for a plug flow disinfection system, right? So depending upon how well you can make the system behave like a plug flow, you can go ahead with it. But depending upon your type of mixing, you can sometimes end up having a series of CSTRs. This is especially the case with plug flow reactors in the context of disinfection, let's say, right? Why is it? Because if I'm trying to bubble through ozone, which is a strong oxidizing agent which can degrade the cell walls and thus lead to disinfection, maintaining the system will typically behave like a CSTR. So to be able to approximate or achieve plug flow reactor system, I will have it in series, or there are different ways to go about it with baffle walls and such too. So that's one aspect to keep in mind, right? So I guess here what do we have? This is for chlorination, simple or typical system. Chlorine is being injected here, Cl2 is being injected here. We have sensors obviously, and different controllers for chlorination and dechlorination. We will look at why we need to dechlorinate the system. So what do we have out here? It's a typical contact chamber for chlorination. Baffles are provided to promote plug flow, right? You want a plug flow reactor as much as possible, because for the same volume, the R net for loss is typically higher. When chlorine has been applied at elevated concentration, right, the concentration of chlorine at the effluent will also be high. And in general, I'm not sure if people experience this now. At least when I was a child back in my hometown, some days we used to get this water and it used to have a pungent smell, and we were worried that there was something off. Yes, it was off, but it's not something that we have not been able to remedy at home. It was that the municipality was pumping in more chlorine than was necessary, we will look at why they add more chlorine in the first case. So, if the chlorine is too high, you want to dechlorinate. So, that is why you want to add a reducing agent to be able to reduce this oxidizing agent, which is chlorine. So, that is what you see, right, typical plant. Yes. So, let us move on. So, plug flow disinfection system, there are different ways to promote it, but this is with respect to typically chlorination. If it is ozonation, you are not going to keep it open to the relevant surface. So, different ways to promote this plug flow, right. We do not want to achieve completely mixed. So, again different baffles, you see the different baffles to be able to achieve plug flow system here, right. Or obviously narrow long channels which are divided, so that again they behave like a plug flow system. So, that is what it looks like typically, let us say. And again different plants and such, let me not go into that in detail, but with respect to ideal plug flow, you want to have length obviously much greater than the width, right, and ratio is typically greater than 40:1, height to width 1:3. So, for example, an example of this particular case was seen out here, let us see. But obviously with the baffles or baffle system, you can try to get around that. Yes. So, here you see with baffles, not here. Okay. So, there is not a great picture here, but the previous ones were better pictures of the baffle based system to achieve plug flow reactors. So, disinfection components, what are we trying to do? So, why is it that the municipality was adding chlorine in the first case? Obviously, they want to kill the or inactivate the microorganisms present. But in the context of my hometown, that was with respect to supplying drinking water. Here we are talking about it in the context of wastewater, let us say. So, I want to inactivate the microorganisms. Though I am discussing this, this is relevant to the water aspect, but let us go ahead and talk about it in general, let us say. So, secondary disinfection. Primary disinfection is what we are looking at in the context of our wastewater. In the context of water, we have to obviously kill the microbes and also ensure residual chlorine, right, maintaining the disinfectant residual. Why is that? For example, at least in the Indian context, let us say this is my water treatment plant, not the sewage treatment plant. Why am I also discussing this here? Because we will again need to discuss disinfection later, rather than doing it in parts. I am discussing that here now. Maybe we will look at it briefly later on. So, in the context of the water treatment plant, this is not the sewage treatment plant, the water will have to be pumped over long distances to different locations, let us say, right. So, you can have microbial growth again, though you apply some chlorine here to kill the microbes here, right, because of this long contact, long traveling time, right. By the time it comes to my home, I can maybe, at least in Indian case, this is always the case, especially in the joints and such. I can have sewage from the nearby sewage lines coming in contact with the distribution network, or penetrating the water distribution network, and thus contamination of the water. So, if there is no residual chlorine or residual disinfecting agent, it is going to lead to, what do we say, transmission of disease, or transmission of or propagation of pathogens there. So, obviously, that is the reason why I want to have some residual disinfectant. In India, it is especially important, right, because our water distribution networks are relatively poorly maintained. So, that is why sometimes you see that you get much more, what do we say, chlorine than is typically acceptable, because let us say if I am living out here, let us say, and there is one person living far out, but they are going to apply the same chlorine dose. So, by the time this water travels here, the chlorine dose might be less, 0.2 milligram per liter is typically acceptable, but here it might be pretty high. Let us say, why? The travel time is less. So, there are different ways to look at it. So, primary disinfection at the point of disinfection, secondary disinfection to rule out, what do we say, microbial regrowth and contamination of the water later on, right, that two aspects. So, different disinfection methods. So, free chlorine, combined chlorine, we look at that, chlorine dioxide, a strong oxidizing agent, ozone, a remarkably strong or the strongest oxidizing agent among these chemical oxidizing methods or chemical oxidants, let us say, and UV, ultraviolet, right? Ultraviolet disinfection. So let's look at the aspects. Okay, before I go further, one aspect to consider is that, as I mentioned, oxidizing agent, oxidizing agent, oxidizing agent, oxidizing. So when I say oxidizing agent or oxidant, what is it that I'm trying to say now? Even in the context of what is this, the microbial degradation of the organic matter, we came across this electron donor, electron acceptor, right? Oxygen, right? Oxidant or oxidizing agent. So strong oxidant would strongly want to accept the relevant electron. So typically it can degrade organic matter. Cell mass is also organic matter. So that's why you are going to add the strong oxidizing agents, which can, what do we say, degrade the cell layer, what do we say, components, or the cell wall, let's say, right? So different ways to bring about the inactivation of the microbes. We'll go about that. But as can be seen, one common aspect among all these top 4 oxidizing agents, top 4 disinfection agents, is that they are all oxidizing agents or oxidants. I think we will discuss this now. Okay, before I go further, so what do we have? Chlorine, ozone, chlorine dioxide, permanganate, chloramine, ozone and hydrogen peroxide, ultraviolet. So here we have different conditions that we want to meet, let's say. Produce trihalomethanes when total organic carbon is present. These were the harmful disinfection byproducts that I discussed about. So you don't want to have these formed. So what are some of the ways or types of disinfecting agents which can lead to formation of these harmful disinfection byproducts? Chlorine and chloramines. Yes, right. So that's one thing to look at. Sometimes with ozone, but that's when there is bromide. So let's not go into that for now. But chlorine and chloramine, which is pretty cheap to use and add, the issue is that you have formation of these disinfection byproducts. In India, people don't consider that to be a huge issue, because if you look at the number of deaths, especially of the infants or the vulnerable population, you will see that most of the deaths, or considerable fraction of deaths, are due to diarrheal diseases. So obviously greater priority is to kill the microbes, and we will think of these aspects which will have long-term issues though, like sometimes at least DBPs are classified as carcinogens according to US EPA. So we will maybe, as a country, once we develop, then we will start looking at that. So that's one aspect to consider though. So they can produce oxidized organics and such. We will not look at that for now. And these are different types of what do we say, pathogens here. Yes, protozoa, viruses and such. Log 2 is at 99.99 removal, 99.9 removal or such. So log 2, that's what it is talking about. So as you can see here, permanganate, chlorine and such, they are not able to achieve, what do we say, a great level of removal for what do we say, quite a few of the pathogens of interest, let's say. So that's something to keep in mind, as in not every disinfectant is effective against the range of pathogens that we come across. So that's one thing to keep in mind. So secondary disinfectant, as in I'm assuming that it's about the relevant residual disinfecting properties. So chlorine, yes. Ozone and UV, certainly not. Chloramine, yes, right. So obviously if I want to have a residual oxidizing capability in my water, obviously I need to choose chlorine or chloramines. So if I add too much chlorine, obviously I know these toxic disinfection byproducts will be formed. Yes. So it's a trade-off how I want to go about it. But sometimes, let's say, you can have ozone to kill the microbes and the trace organics, and then you can add some chlorine so that the DBP concentration will be less, but you will have enough residual chlorine available, let's say. So let's dig deeper into this aspect, let's say, right. So here we see CT, or intensity time. So earlier people used to maybe just mention concentration, or just mention the time required for disinfecting a particular kind of microorganism or pathogen based on applying a particular kind of oxidizing agent. But now, as we know, both concentration and the time are relevant. So here this is called the CT approach. So it will give you an idea about how much concentration and the contact time is required, let's say, right. So that's the approach that is widely accepted. So for combined chlorine, you see that again with respect to a range of viruses, yes, it's doing fine. But with respect to, let's say, Giardia, right, and there is something else that should be missing out here. So I'll come back to that. So there are some kinds of what do we say, pathogens that lead to diarrheal diseases, a major cause of deaths in India, a major cause. So for that you need to have a lot of contact time, let's say, or high concentrations and high contact times, as you can see here. But within acceptable, what do we say, times and concentration, CT values, you see that most of the viruses are, or a few viruses can be inactivated. So free chlorine, again the issue is that most, or compared to combined chlorine, it can inactivate a range of pathogens, but the issue is that you will again need to have high CT. So more contact time is required. So that's obviously an issue. Chlorine dioxide, again you see that relatively lesser contact time, but it can't look at Giardia, Microsporidium, if I am not wrong, and these are typical aspects. Though we mentioned Giardia, it's not particularly effective. But with respect to ozone and UV, and this is the advantage, I guess, you see that they are effective against a range of, what do we say, pathogens, and that too at relatively less CT values, right. So contact time is particularly or relatively less out here. So this is an advantage, because to kill a range of pathogens, I need not, what do we say, spend a lot of time, meaning a lot of resources and space, but I can what do we say, do this within a smaller time, and also that will affect the size of the system. But one aspect when we are designing small reactors is that it is easy for the water to bypass the relevant treatment, what do we say, path, and short circuited from influent to the effluent, meaning it does not spend enough time in the reactor. So short circuiting can happen in shorter or smaller reactors. That's one thing to keep in mind. But ozone and UV relatively more expensive, and but one aspect to keep in mind is that with UV the capital costs are coming down, because more and more people even in India are using that or trying to adopt it. For example, it's similar to the cell phones. Earlier the costs were high, now they are coming down because there is more demand, and thus the logistical chains and infrastructure is prepared so that the cost per, what do we say, cell phone comes out. So this is for 99% inactivation. Again, ozone and UV, they are remarkably good at inactivating Giardia and Microsporidium, which is not the case with what do we say, typically combined chlorine, chlorine dioxide and free chlorine. That's something to keep in mind. Let's move on. So chlorine, as we mentioned, is an oxidizing agent. It acts by oxidizing the cell wall of the microbes. Cell wall, organic matter. So you have organic matter which is relatively more reduced meaning it can give electron or it can donate the electron, and you have chlorine which is a strong oxidizing agent, it wants the electron. So thus it can, what do we say, if I use the layman's terms, eat away the cell wall. By eating away the cell wall, the contents of the cell, they are going to come out, and then obviously the relevant pathogen, depending on the type of pathogen, because not all pathogens obviously have cell walls, they will not be able to thrive, let's say, or function. But one aspect to keep in mind is when we were looking at bacteria forming of flocks and such, we saw that, and during the endogenous phase, right, we saw that bacteria have a slime layer, and if there is a slime layer, that acts as a protective layer or coating for the relevant microbes against chlorine. Chlorine has to eat away all that or oxidize all that slime layer before it can get to the cell wall. So endogenous phase typically occurs later. So relatively older microbes, if I can say so, older microbes, they obviously need higher concentrations or higher contact time before they can be inactivated. These are the aspects obviously you need to be aware of, especially when looking at oxidizing agents like chlorine and such, let's say. So what do we have? The primary action is oxidizing cell walls, and then what do we say, damage to the relevant cell ingredients, let's say. It can be applied in different forms. Cl2, remarkably cheap, but one issue is it's a fire hazard, toxic hazard to the people there. So the kind of application is going to obviously depend upon what we say, how well you enforce the fire hazard standards. In India, maybe not a lot, that is why people go for this, and it's pretty cheap. Or it can be applied as NaOCl or CaOCl2, let's see, right. So let's look at the relevant reactions. Okay, before I look at the relevant reactions, let's compare the effectiveness. Here, when I form NaOCl or add NaOCl to water, what is it going to form? It's going to form OCl minus and Na plus, right? And this OCl minus will be in equilibrium with HOCl. So HOCl is a much more stronger oxidizing agent when compared to OCl minus. Obviously, it's dependent upon the pH. We will look at this later. But just to, what do we say, convey the information or message that HOCl is a much more stronger oxidizing agent, we have this graph. So here we have the effective chlorine concentration on the y-axis and the contact time or minutes on the x-axis. Chlorine concentration versus contact time to achieve 99% kill of the E. coli, right, by various forms of chlorine. As you can see, let's say for a particular concentration, let me say this. You can see HOCl requires very little time, OCl requires a lot more time, and this combined chlorine NH2Cl chloramines require much more time, let's see, right. So I guess this should have been 1000 because this is logarithmic scale, 1, 10, 100, 1000. Each time it's 10 times higher. So you can see that HOCl is remarkably effective. And let's say for a given time, let's say 10 minutes, you can see that the concentration of HOCl required is much lesser compared to the concentration of OCl minus that's required. So obviously we have to play around with the pH to maintain, what do we say, favorable concentration of HOCl, but you can't bring the pH too far down, let's see. Okay, so I guess I'm almost out of time, or rather exceeded my time limit. So I'll end today's session and continue this in the next session. Thank you.